All right, guys, it looks like we are right at the top of the hour, so I'm going to go ahead and get things kicked off and introduce everybody. So thank you, everybody, for joining. Um, Today's session, of course, is about on-premise or in the cloud, addressing trends in public safety. My name is John Joseph. I'm going to be the moderator for today's session for Datamark and the team. Before we get started, I'd like to let everybody know that we will be recording, or we are recording this webinar, so that way it can be saved for later, and that all of the attendees are muted currently in order to kind of ensure that quality assurance. I myself am going to drop myself on mute here in just a second. But if you do have any questions you want to be able to go through and ask, the platform you see here at the bottom of your screen has a area where you can go through and submit questions or put in chats and so forth with the team. So feel free to go ahead and do that. And I'll try and make sure we make sure that the folks who are doing the presenting get a chance to see what questions are coming up, or we'll try and answer them at the end. I'd also like to just take a quick second to thank our sponsors for the virtual conference, the folks from Critical Response Group, CRG, and of course our friends at Comtech. It's kind of interesting, both of those presenters, or both of those vendors, are going to be speaking at tomorrow's sessions. So if you get time to go ahead and sit in on their presentations tomorrow, I would really highly encourage that. For today's presentation, I'm joined by two of our most valued partners in the public safety industry, John Persano and Doug Gardner from Amazon Web Services. And with that, I'm going to stop talking, hand it over to Doug and John so they can go through and start their presentation. Thanks, guys.
Thanks, John. Hey, everybody. Thanks for joining us today. Appreciate your time and energy as we go through this session. My name is Doug Gartner. I'm a Principal Solutions Architect here at AWS. My background is in data engineering and big data architecture. I've been with AWS a little over 4 years now, focusing on public safety use cases. And we're really excited to talk to you today about the trends in public safety with AWS. John?
Thanks, Doug. Hey, good morning or good afternoon, everybody. John Persano. So I lead the 911, the fire, and EMS subvertical within the Amazon Web Services Justice and Public Safety team. I've been with AWS for about 15 months. Background is as consulting in public safety and in the private sector, and military liaison between public entities and the Department of Defense for disaster preparedness and response. Very excited to chat with you all today. Hope we have some great questions. And I think we're ready to kind of get the ball rolling, Doug, if you want to hit the next slide. Okay, so briefly, some of the topics we're going to talk about today. We're going to talk about the impact of next generation 911 and how it impacts the on-premise versus hybrid versus cloud discussion. That's going to kind of shape where we're going to go today. We'll also talk about what's the public safety ecosystem and how we define that, and how next generation 911 can shape the future of public safety. We'll hit on topics surrounding the transition to or adoption of cloud technologies. And we'll also hit on the importance of where data is stored and how it can be leveraged as it relates to maximizing the information available today, and some of the barriers that may be precluding people from taking advantage of new solutions to existing problems. And then we're going to wrap it up. I'll leave at least 10, if not 15 minutes, hopefully, for questions and answers. And that's really where we want to focus our time if we can. And we would love to have you all put those in the Q&A, which is at the bottom of your Zoom screen. Or if you need to, you can put something in the chat. We'll be watching both the Q&A section as well as the chat section. So next slide, please. Okay, so what is NG911 and why is it so significant? Next generation 911 allows us to serve the public in a manner that's most familiar to them, and that's primarily through connected devices. So unlike our old Ma Bell, where we were limited to just what the caller is saying, only voice communication and a single location, we now have access to nearly endless streams of information. So while that brings tremendous opportunity and possibilities, which are very exciting, it also could be a bit daunting. So I'm going to kind of lay the groundwork here, and then Doug's going to dive in a little bit deeper, much more deep, into the technical aspects and why there's a difference between premise, hybrid, and cloud, and what may be the best fit for some of your challenges and use cases. So at the core of next generation are, of course, location and GIS services. So now with NG911, not only can we have improved caller location, but we can also validate and verify call and incident information through geo-rectified sensors. It could be something as trivial as a camera, car telemetry, or a personal location device. So that level of location detail can now be provided to responders in manners that weren't dreamed of earlier to make a better informed decision and expedite the decision-making process, which is going to directly influence the public safety ecosystem, which I'll talk about here in the next slide. Slide, please. Okay, so for decades, public safety has really leveraged a rather linear workflow due to the limitations of what technologies were available and how those technologies were leveraged. So let's think about, how that public safety workflow works. So you start off with a 911 call. That 911 call is routed hopefully to the right 911 center. And once it's received, then the call taker will take the verbal information and then start entering information into the computer-aided dispatch. And then the dispatcher will take that over, send out a response via fire, medical, et cetera, and then that response leads to some kind of resolution. Somebody goes to a hospital, somebody goes to jail, and then there's another system that they'll enter data into and take that information, such as jail management systems or hospital admission systems. And then there's a resolution at the end. So for 911 specifically, when we discuss location and GIS capabilities, that's going to allow us to rethink how that ecosystem works. So instead of going from 1 to 2 to 3, how can we actually leverage new technologies to expedite that decision-making process and change the workflow? So now we're shifting from a linear response model to a more dynamic response model, with the location being the starting point. So think of it this way as the closest unit dispatching. So right now, many areas do not have the technology to understand who is out in the field, what their capabilities are. So 911 call comes in with improved geolocation and GIS capabilities. We now can look at who is nearest to the incident, who is most prepared for that incident, and dispatch somebody who is closer and save time and save a lot of, possibly expediting that response process. So when we look at the capabilities, we could even determine what kind of vehicle it is, what the capabilities are of the vehicles, what the skill sets are of the individuals within the vehicles. And that's all part of next generation 911 as we learn to bring in and to leverage these new technologies. So all this 911 data lays the foundation for a response. But unlike today, it can be shared by multiple entities simultaneously and really disrupt this workflow. And that's what we want to talk about, is how can we make more informed decisions more timely? So this all sounds great, but there's several challenges. And before we move on to the challenges slide, my apologies, I should have done this one slide earlier. We have a very quick poll that we would like you all to take. And John, if you don't mind bringing that up, if possible.
Uh-oh. Let's see here. All right, can you guys see that on the screen?
Not yet.
Let's try and launch the poll.
There you are. Yep.
So the poll is pretty simple. We just want to know, how would you describe your role, your organization? I know we've got, well, probably about 80 some people that are on here right now. So we'll give you guys all a chance to jump in here and put in your 2 cents. Like I said, John, my favorite part is watching these numbers climb, and you know that people are paying attention. All right, getting right there. We're starting to slow down a little bit as far as the numbers. But I think that's about 75%. I think we can go ahead and we'll lock it in there. Okay, so we'll end the poll.
Perfect.
And I can share those poll results. Oh, I should be able to share those poll results with everybody. Unfortunately, it does not look like, oh, maybe it did. Can you see those poll results? Perfect.
Absolutely. Yep, 68% GIS, awesome. And so thanks everybody for taking the time to do that. We have one more quick poll, which will be after this next slide. And that helps us kind of gauge where we are and what we want to focus on. So thank you for that. So Doug, can we hit the next slide? And then that will be my last slide, and then I'll be turning it over to Doug. So we talked about what's in the realm of the possible and how we can use location-based services to inform the decision-making process and all the sensors and opportunities that are out there. Well, these don't come without challenges, of course. So the number one challenges would obviously be connectivity. So I'm not going to dwell on the connectivity challenge because Doug's going to take that in more detail. But all I'm going to do here is highlight the fact that in order to leverage these connected devices, one must have reliable connectivity to perform the stated tasks. And as many of us live or work in areas where connectivity may be inconsistent, that inconsistency may have led us to not even entertain the thought of looking at how we can move to a hybrid or cloud services and just staying with what we have on-prem because we're very concerned about our connectivity. And Doug will talk a little bit more about that. For bullet point 2, very straightforward. The rate of technology expansion, pardon me, often outpaces the ability for public safety to digest it. So put simply, many response agencies, they simply don't have the personnel and the time to stay abreast of capabilities that exist or are being developed. It's not unusual when a public safety entity is looking at a new technology or upgrading an old technology. One of the first steps is to look to your neighbors, find out what they did, and take their RFP and copy and paste it. And you know, that knowledge base of people who are very in tune with what's in the realm of the possible can be limited in some public safety organizations. So that's an issue that we have to think about and have to address. Then we also have the information overload. That sheer volume of information available today can even overwhelm the most ardent supporter of technology adoption. So far too often, we're going to take this road that because we can, we should. We have access to these information streams. We need more information. Now we start bringing in that information and it's overwhelming. So what do we tend to do? We tend to shut down because we're overwhelmed with the amount of information. So Doug's going to talk about a couple of ways to mitigate this challenge in more detail. And then lastly, you know, historically, we think of interoperability. We think of these one-to-one interfaces, right? This system or database needs to share information with that system or database. With the volume of information sources and solutions that are available today and will be available in the future, we simply can't continue down this path. We have to come up with ways to use technology to identify what information is needed, by who, for what, in what format, and at what interval. And I'm going to turn it over to Doug here after the next poll. And Doug's going to discuss how cloud technologies can help leverage what is available in a manner that's least intrusive and provides the most support to the decision-making process, among a couple other topics that Doug's going to hit. So John, I think we want to do the last poll, and then I will turn it over to Doug.
All right. Launch that poll, I believe.
Yes, sir.
Okay, pretty solid at our 75% there. All right, I will end the polling. I will share the results, maybe.
We got him.
There you go.
Excellent. Thank you,
Awesome.
John. Appreciate that. Doug, turn it over to you, sir.
Thanks, John. And thanks for that. Thanks for answering that poll question. It really helps gauge the sort of next portion of the discussion. So a lot of this is going to be a little, well, some of this up front will be review for some of you, but let's just make sure we're all on the same page when we're talking about the different nomenclature for on-prem and hybrid and cloud. So when we think of on-premises, that's the traditional way to consume IT resources, right? You have either physical machines in your office, in your location, or at a data center nearby or a co-location facility nearby, And those are where you consume your resources. So whether it be virtual resources, like you have some really large scale hosts and you're sort of chopping them up and giving out virtual resources to the different applications necessary to power your mission, or whether they're just physical resources and you're not using any virtualization, you're going straight to the bare metal machines to again power your applications. That's what we talk about when we're thinking on premises, very traditional. You have a physical machine, you could turn it on, turn it off, that kind of thing. We'll skip hybrid for a second and go to the right-hand side, which is cloud. If you're looking for like the textbook definition of cloud, it's the on-demand delivery of IT resources over the internet with pay-as-you-go pricing. So in layman's terms, that really just means that you get the same machinery, except instead of it being physically present in your office or down the street in the data center, it's present somewhere else, and you're consuming it over a connection. Now, whether that connection be standard internet through your internet service provider, whether that connection be over the air, which we're seeing a lot more of and we'll talk about, or whether it be through some sort of dedicated direct fiber, which is a really common way to consume it. And in that case, with dedicated direct fiber, you're not actually going over the internet. You're going over dedicated fiber, but you're still connecting to a location that's not, in your back office. Now, we see a lot of customers in public safety, a lot of agencies going to a hybrid solution. And the reason for that is because you kind of want a little bit of both. And most of your applications can be hosted in the cloud, but you need some computing power at the edge to power some of your really low latency workloads, to do things where you're trying to keep some of that data local for different performance reasons, things like that. So hybrid really just means a blend of the two, where you have some sort of physical local presence of machines, local presence of IT infrastructure, and then it's connected to a cloud-based service. Sometimes you'll hear the word hyperscaler. That's referring to like AWS or Microsoft Azure or GCP, which is Google Compute Platform. But again, a cloud in this sense is just not next to you, right? It's somewhere a way that you're connected to over the internet or over that sort of dedicated fiber, dedicated link that could be private connectivity. So some of the focus areas that we're going to talk about are reliability. This is hugely important. We all know, if you have a single place where those applications are hosted, it's going to go down at some point, right? There's only so much you can do to try to use UPSs, to try to mitigate for floods and fires and all sorts of different natural disasters and lightning strikes and all that good stuff. So you're going to need to have multiple locations where you're hosting these mission critical applications. And that's one benefit of the cloud. And we'll talk a little bit about that in more detail. Connectivity, hugely important. So you're only as good as your linkage point to it. You could have the most robust, most reliable, most scalable application sitting in the cloud. But if your link to that is very finicky, very fragile, then you have a trouble, you have a challenge. Because now when you're connecting to that, if you have to go restart your router once a week, that's not a good feel, right? You want to be able to connect to that reliably. So that linkage point becomes a really key piece in making sure that you're having the kind of availability and the kind of reliability that you're looking for those mission critical applications. Then we're going to talk a lot about data and analytics. Thanks for answering that first poll question. I saw many of you are GIS analysts, so this will be, I think, something we'll focus a little bit more on, which is less on the application build out and more on how do we get more data and more analytic output to help power our mission. And then lastly, the role of chaos engineering. And this might seem a little bit, not like the others in terms of the topics we're talking about, but we really wanted to emphasize this because this is something that's hugely important as we have that paradigm shift that John was talking about. So as we move away from hoping or designing that, nothing's going to fail and everything's going to be up all the time, moving towards a way of embracing failure, knowing that everything at some point in time is going to fail and that's okay. And not treating that as a bad thing anymore, but treating it as a commonality and a thing that's going to happen. And if we can embrace it and handle it gracefully, we don't have any hiccups in our application. They keep moving and powering the mission. So to dive in on reliability and connectivity, this is important, and we want to make sure we want to help scope these workloads, right? So different workloads need different needs for connectivity. Some are okay with intermittent connectivity. For example, there might be an application that's hosted, out in the middle of the sea, in the middle of the ocean, right? you're going to be okay with periods of intermittent connectivity, and that's okay because the application that you're connecting to is designed to handle that. So for some of the GIS people in the audience, you'll know that it's like, okay, I'm not going to have this kind of constant stream, really robust, low latency connection to what I'm looking at. That's okay. I'm designing my application such that going through periods of this, intermittent connectivity, I can still get live updates from the application that I'm connecting to. And that's important. So you have to really know the application needs. Some applications do require live, constant, consistent, low latency connections. And for that, we have different, purpose-built solutions, right? You might want to have more of that like hybrid style approach where you have a physical presence local to connect to. You might have something that's more of a local zone or local to your domain, again, to have that low latency. But again, the idea there is that robust connectivity because the application you're connecting to requires that strong form of connectivity. So when you're determining needs, you want to start from the application and work your way backwards. What is that application designed for and what type of connectivity does it need? There's different metrics to focus on there. One metric is latency, and that's usually key in public safety. We see that as the most dominant metric. Because again, if your latency, you may have really high bandwidth, right? 500 meg or 1 gig bandwidth, great. But if your latency is at a constant 300 milliseconds, then it's hard to make some of those real-time decisions that you need to make. And so getting the latency down to 20 milliseconds or 30 milliseconds, and then making it so that you can make those decisions much quicker is better. And thanks for Rachel for that question. So a simple definition of latency would be the time it takes for you to connect to something and hear back. So if I make a request, if I click a button and say, I want the answer, I fill out a form and I want the answer to this, if it takes 20 milliseconds round trip, that would be your latency for that response. If it takes 300 milliseconds or 3 seconds or 3 minutes to come back, then again, you're back to, I can't really make my mission critical decision with a 3-minute response time when I need 30 millisecond response time to answer my question. And so latency becomes so dominant when we're talking about these use cases because of, again, the real-time nature of a lot of what the folks are listening to do, right? The mission critical needs, making those real-time decisions as opposed to, sending off my analytic and hoping it comes back in a timely enough manner where I can then impact and make the right decision. Thanks, Rachel, for that note. And Dallas sent a great question as well earlier about ride sharing applications, and we'll talk about those in detail. Thanks, Dallas, for that question. Okay, so again, distinguishing amongst available options. In the past, your options were, hopefully there's fiber where you are, right? I can get a fiber connection to my office. I can get a fiber connection to my data center. That's great. And that's still a really ideal state scenario because dedicated direct fiber, it doesn't have the same limitations that some of the if you're going over the public internet, you might be have some challenges with sharing of that bandwidth or other things like that. So dedicated direct fiber is a great way to go. However, it's not the only option. As in the last, I would say 2 years, we've seen a lot more connectivity modes that are dominant wireless. So instead of, in the past, if we said your primary means of connecting to a mission critical application is going to be over the air, we'd be like, it's a non-starter, right? We're not going to do that. But over the last 2 years, we have a number of agencies who their dominant means of connectivity is using LTE or a combination of LTE, 5G, satellite, microwave, instead of laying fiber to some, really rural areas or areas that don't have the fiber infrastructure supported. Over the air works really well. And so again, you can sort of distinguish which option might make the most sense based on the geography you're in. And that really helps. So again, just to say that there's a paradigm shift for moving towards wireless being the primary means of connectivity. When you're talking to your providers, again, you want to ask those questions. What type of latency does your application usually have? What can I expect for response times when I'm making a query to the application or looking for an answer? And it's not always a limitation of connectivity. Sometimes it's a limitation of the application. Even if your connection is really robust, the latency for the application, the time it takes to answer the question that you asked might not be acceptable or might be good enough. And then lastly, in terms of other metrics, looking for how much bandwidth is required, what if there are other shared workloads, all of that is really helpful when sort of designing out the necessary network infrastructure to power these mission critical applications. Okay, so shifting gears a little bit into data and analytics. So I spent a number of years designing big data systems on premises, and it was great. We would have 100 node clusters, 200 node clusters, 500 node clusters, and it worked really well. The challenge is that's really expensive to do. Racking and stacking all of those machines, building them out, doing hardware refreshes, changing out hard disks, all of that stuff is a really heavyweight operational overhead. And you run into the challenge that you're sort of in this constant state of doing hardware refresh cycles. And that it works for a time period, but over time you run into that burden of, again, I can't keep up with the demand on the infrastructure. And I have a ceiling. My ceiling is whatever I purchased. If I have a 100 node cluster to analyze data, that's great. What happens if I need another 50 nodes? Well, I can go procure them and go through that process of, building out another 50 nodes. But what if I only need them for a month or only for a week? Or what if I only need them for one analytic that I'm trying to run? That's where you run into the challenge of, okay, am I going to buy 150 machines to just run one analytic? Or am I going to use sort of ephemeral infrastructure where I can ask for 150 machines for a few hours, run this really heavyweight analytic, and then turn those machines off? So the analogy holds true here, the sort of power company analogy, where whenever you turn the lights on, you're charged for the lights. You turn the lights off, there's no electricity charge. The same holds true for the cloud consumption model. If you need a lot of machinery, a lot of power to answer your sort of heavyweight analytic questions, that's totally fine. You can sort of rent that out for a period of time. And then when you're done, you turn it off and you're not on the hook for it anymore. And it's not sitting there sort of, not you have something to deal with, right? Performance is a big thing. So if you were to buy on-premises machines, usually you scope them out or spec them out to be homogeneous. So you'd have a number of, 64 core, 256 gig memory machines, and they all look the same. And that's because the standardization is necessary to keep things running, to keep operational tasks smooth. But what if you need some GPU optimized machines? Or what if you need a different type of chipset or a different type of disk or volume? Now you run into the challenge that you're going to sort of force fit a workload that's meant to be run on GPUs on something that doesn't have that power. And while it might work, it's clearly not optimal and will create additional burden. So you can have purpose-built machinery that you need to answer specific analytic questions. And again, the poll, really appreciate you guys answering that. The number of analytics that GIS is going to ask for GPU optimized machinery or more powerful machinery, obviously you're going to need more power to answer some of those analytics. So again, really dealing with the fact that purpose-built is much better than one size fits all. And you can get that if you have sort of the abundance of infrastructure at your fingertips. Scalability is something that we really want to emphasize. I mean, there's always going to be a ceiling when you're talking about on-prem. And so a lot of agencies will do, again, that hybrid solution. You might have a little bit of infrastructure on-prem to do your low latency or other type of workloads. And then you have the sort of cloud at your disposal for some of those heavier weight questions or more operational tasks that require, like a monthly report or a quarterly report, where you don't want to be on the hook for that infrastructure just to run a report once a month. And then capability. So John mentioned or touched on this a little bit before, but the pace of innovation matters a lot here. So as, whether it be AWS or another cloud service provider, as they come out with more capabilities, you can just benefit from that and consume those new capabilities, as opposed to if you're on-prem, again, it would be a whole upgrade process, right? You have to go through procurement and licensing and all that good stuff. Whereas if you're consuming a service in the cloud, you can sort of keep up with that pace of innovation and some of the more modern ways of approaching analytics and large scale data analysis you can take advantage of. Okay, so I wanted to talk a little bit about a modern data architecture that we're seeing a lot of. And really the key message here, the key highlight, is that there's no one size fits all. No matter how much we try to standardize on data lakes or data warehouses or relational databases, and I know the GIS folks will hopefully agree with me here that one size fits all doesn't work. If you try to force fit GIS data in a traditional RDBMS, unless your schema is extremely well designed, it's going to be hard to get the answers you're looking for in a timely manner. So there's purpose-built databases that will work better for that type of workload, or purpose-built add-ons for a traditional database that kind of repurpose how the data is stored under the hood. And that's really, really important when you're talking about doing specific analytics. Again, GIS being one of them. If we force fit that into, a standard SQL database, I've seen that a number of times where it'll work, but again, it's probably not the right tool for the right job. And you can make it work much better if you're using the right tool. So what I wanted to highlight here is that it's always a good idea to have some sort of central repository to keep raw data. That preserves data lineage, that preserves integrity, that preserves the data provenance that you want to have, so that if you ever need to go back to that raw to ask a different question of it, or normalize it in a different way than you did initially in your ingest process, it's good to have that. And the benefit here is that storage is cheap. So thinking back to my time, 10, 15 years ago, if we tried to do that, it's like, well, you only want to have one copy of the data, right? It's got to be the gold source. This is the copy. And we're trying to optimize for storage because storage wasn't super cheap. It wasn't super cost effective. That's changed. That paradigm shift has changed pretty significantly, such that you can have multiple copies of the same data that's purpose built in a different way to answer a different set of questions. So for example, you might have one data set that's coming in that you're pushing into a NoSQL-like database for key value lookups, or distributed key value store type of answering of questions. So if I need to do a needle in the haystack query, I'm looking for a few line items out of a trillion records. NoSQL is going to work much better than a traditional relational database for that. However, I might need to use that same data set to power a machine learning type workload, or that same data set for a more traditional data warehousing type reporting workload. I can push that into a NoSQL database and push it into a data warehouse and push it into a machine learning system. And it's the same data under the hood, but I'm answering 3 different questions with 3 different purpose-built tools. This is where I think the true power is, and what we want to emphasize. And that when we talk about data lakes, it sounds really cool, but really the power of a data lake is not the storage of the data. It's the after the fact tooling that you can then bring in and consume. And you can always change your mind, because as we all know, these use cases are evolving. Soon enough, you'll ask a different question of the data than you asked 6 months ago, and you want to be able to go back and ask that different question. And maybe you need a different tool to ask that question, whether it be a log analytics tool, or a natural language processing tool, or a machine learning tool, or a warehousing tool, or even a relational database. It could be a traditional workload. That's totally fine. That can consume from the data lake as well. So really emphasizing that a modern data architecture is embracing the right tool for the right job approach, instead of force fitting everything into the same database that we always use, and then getting mediocre performance out of every workload, as opposed to optimal performance out of very specific types of analytics and workloads. And by doing so, it sounds like, oh, well, the cost is going to increase significantly. But what ends up happening is the cost actually goes down. And this might sound like a little bit of okay, wait a minute here. But the reason the cost goes down is what ends up happening when you use that traditional database to force fit all the data, you scale it up. You throw more memory at it, more disk at it, more CPU at it. Now you vertically scaled that, such that you have a really big, bad machine that's very expensive, very hard to maintain, takes a lot of effort to keep that thing alive and healthy and all that good stuff, because it's like this big, bad database, right? Whereas if you are purpose building it, you have a lot of smaller machines that are purpose built to answer questions. And those purpose built smaller machines in aggregate don't add up to the same cost as that big, bad machine, right? Because they're purpose built to answer a specific question, as opposed to scaling up because they got to answer all the questions with the same tool. So we can talk more about that, but just to emphasize the fact that by purpose building, by using the right tool for the right job, you can actually optimize for cost, because you're not, overscaling to answer a question that probably shouldn't be answered by that system. Okay, switching gears one more time, I wanted to talk about chaos engineering, and this is pretty different than the last 2 topics that we touched on, but it's really important. So in the past, we always designed systems to never fail. We have uninterrupted power supplies. We have, different floodplain mechanisms to block floods. We have firewalls. We have, all the different things, so that if there's someone cuts a fiber, someone cuts a network cable, we get hit by a lightning strike, there's a flood, there's a fire, that we have some way of keeping the lights on. That was the goal, right? But the paradigm shift has really helped us realize that that's a never-ending battle. And at some point that those machines are going to fail. And you don't know why. There could be combinations of reasons, but at some point those machines are going to fail. So what chaos engineering does is say, okay, let's assume they're going to fail. Let's assume that, you know, someone's going to pull the power cord by accident, or, you know, we're going to get hit by a lightning strike, and that machine's going to fail, or that disk is going to fail, or that chip is going to fail. What's going to happen to the application when that does fail? So chaos engineering is the idea of actively injecting failure, actively injecting fault into your application, such that when it happens, it becomes transparent to the end user who's needing to use that application to power their mission. So an example of that might be, I have my application hosted in, you know, an availability zone A and availability zone B, and I'm going to go ahead and kill the machines in availability zone A. And that's simulating, it's an exercise, right? It's an experiment where it's simulating a power failure or a network failure or connectivity failure, what have you, in availability zone A. What happens? Does availability zone B still have enough power to power the application? If it does, great. Then my end users, they don't know whether they're connecting to a machine in availability zone A or a machine in availability zone B. All they know that they're connecting to is, you know, GIS data, right? And I'm going to go get that data, and whether I get it from here or here, I don't care. I'm connecting to a single load balanced endpoint, and it's going to point me at the healthy machines. So the idea is, unless you test that, unless you run these chaos experiments of what happens if this fails, what happens if that fails, circling every single point of failure on the architecture with a red marker, and injecting fault, and then seeing it fail, then you can't be sure that your application is going to stay healthy through some sort of, you know, chaos that happens. So what that looks like is you have steady state, you have a hypothesis, which is, if this fails, I have another backup copy, or I have something else that's going to pick up the workload in a seamless, automated way, so that there doesn't have to be, you know, someone woken up at 2 a.m. to swap over a DNS. So when that fails, this should just continue on working business as usual. That's my hypothesis. Let's run that experiment by actively injecting fault, killing these machines. Then let's verify that it does actually work. And if it doesn't, and we've identified some gaps, let's improve and continue to do that process, right? So the idea here is that we take on a different approach to designing a system where it's never going to fail, into knowing that every component at some point in time in that application is going to fail. And that's okay. We're embracing it. And we've actively tested it to know that when it does fail, that's okay. We're going to recover from it in an automated way. And again, our mission will continue working without being impacted by external factors. So to look at that, what that looks like, it's a lot of words on this slide, but I really just want to focus on column 1 and column 5. So when you think about column 1, that would be single points of failure all over the architecture, right? I have a single linkage point between two machines. I have, you know, a single machine powering an application. I have a single database with no backup that's only copy of the data. That would be a sort of maturity level 1. And when you run into that, again, all you have to do is run an experiment where you kill the connection to the database, and now you have a problem, right? Number 5, fast forward to the end, let's try killing the connection to the database. Do I have another database? Do I have another connection? Like, what happens to the application? Does it continue to stay alive? What happens if it does stay alive? Great. Now let's try killing the database itself. It's another experiment we're going to run, another fault that we're going to inject into our application. And all of this should be automated. So it should be sort of self-healing, if you will, where no matter how much I put into it, it continues to operate business as usual. Obviously to an extent, right? Like, you could kill everything and then it's like, okay, well, now it's not working. But injecting failure into single points of failure and knowing that there is, again, another way to continue working on empowering the mission. So I thought that was really important. And I did want to touch really quick on what Dallas mentioned earlier. So the rideshare app platforms, they all do this, right? So Uber and Lyft are hosted on AWS. They use AWS to power a lot of their applications. And when they do these types of experiments. So they'll go test and kill machines they'll go test and turn off connectivity to certain things and make sure that the applications stay healthy. But again, those are two good examples of applications that use purpose-built tools, but also run chaos engineering experiments. So it's a good good point to bring up from Dallas, that like when you're talking about the popular ride-sharing apps, they use these very same paradigms to make sure that they stay alive, they stay healthy. And it has happened where behind the scenes, there's been some sort of application failure, infrastructure failure, what have you, but it doesn't affect the end user's ability to request the ride, to work with the application. They don't know which machine they're connecting to. They just know that they need to get the service. And that service is then, again, being chaos engineered to inject fault and failure so that it continues on business as usual, regardless of failures behind the scenes. So thanks again, Dallas, for that question. And then I think we wanted to leave about 10 minutes for Q&A here. And again, we really appreciate your time.
Yeah, that's great, Doug. Thank you so much for jumping in here and doing this. We haven't got any questions in the Q&A section, although I know that you guys have been chatting back and forth. And thank you everybody for kind of putting in your information and so forth. I think that was great. Dallas and Rachel did a good job there. Let me ask you a quick question there, Doug. Can you talk a little bit more about the time frame associated with transitioning from an on-premise workflow, of applications to those of a native or hosted cloud environment?
Absolutely, that's a good question. So there's different approaches to leveraging the cloud. Some agencies choose to do what's called a lift and shift model. And that's pretty self-explanatory, but what it means is that instead of going out and buying new hardware and then, upgrading that hardware, because we all know there's hardware refresh cycles, and if you don't want to go through that process anymore, that's totally fine. You can procure the infrastructure to power the application through, say, AWS to do that. And what you're doing there is you're just lifting and shifting. You're just picking up that application that was normally hosted on premises and you're pushing it right to, say, AWS, and then you're consuming it in the same way you did before, except instead of connecting to a data center, you're connecting to AWS. That is a really common thing that we see. But there's a slider window here of lift and shift all the way to cloud native. And cloud native, we could sort of go in depth about what the definition of cloud native means, but really at the end of the day, it's consuming more higher level services that mean that you're taking more advantage of the power of the cloud and the nature of elasticity and agility and spinning things up when you need them and turning them off when you don't, to really optimize for efficiency and not having to just have, a lot of wasted CPU cycles. Because what happens frequently on premises is you have to provision for peak. So you buy a whole bunch of infrastructure and now you're sitting at, really, really like heavyweight infrastructure, but your normal business operations might only be 30% of that infrastructure. So now you have 70% of that sort of bloated space that is necessary because you're going to need to power it. Again, if you go into the cloud, you can sort of turn that 70% off. And that might not be lift and shift. That might be like a gradual step 2 or step 3 towards cloud native. But turning the lights off, turning the resources off when you don't need them and not paying for them when they're off. And then moving towards cloud native would just be sort of always spinning up and spinning down. And you can think of cloud native being something like Netflix, right? Where Netflix will spin up when they need the infrastructure and they'll spin it down when they don't. And there's a very cyclical curve that you can follow on, the Netflix usage, that they spin off infrastructure when people aren't using it. So it's a really a way to optimize for the benefits of this pay-as-you-go pricing and the ephemeral nature of machines that are powering your application.
Gotcha. Thank you. Thank you. It does look like we got a couple of questions that come through. Let's start with the one that's in the Q&A, because I don't know if you've got that one up. Have you had any experience with IL5 applications and location latency?
Yeah, so IL5, like DoD IL4 and IL5, is that what they're referring to? I think. I don't want to make that assumption, but we can host FedRAMP High, DoD IL4, IL5 workloads in our GovCloud regions. And so if you're hosting in those regions, it would be kind of your connectivity to those regions. So in terms of latency, it's really going to depend on the connection. We have a GovCloud East and a GovCloud West. GovCloud East is in the Ohio region. GovCloud West is in Oregon, roughly. And when you're connecting to those, obviously your proximity to those matter, but at the same time, if you have direct, say, dedicated fiber, your latency will be very, very low because you're not sharing that bandwidth and you're not going over the public internet, you're going over a private fiber line to the application. So for IL4, IL5 type workloads, as long as you can get to the GovCloud in a strong, reliable, performant way, your latency will be very, very low.
Excellent. John, I think we got another question there.
Yeah, so Dallas, thanks for the question and clarification. I hope I could answer it appropriately. So what we're driving at there is really looking at how are we leveraging all these new sensors and all these new pieces of information and the challenges of doing that if you're very much tied to on-prem solutions. It becomes extremely, extremely difficult to bring in all those different feeds, to analyze those feeds, and to make informed decisions, particularly when you're talking about leveraging machine learning and artificial intelligence to do so. So what we were kind of alluding to there is, just think of a geofence, right? So I have a geofence and I'm pulling in all those sensors. And as I get information, I am telling the software, this is what I need to make an informed decision. This is the type of format I want. And through AI and ML, it's giving you, hey, there's a 75% probability that this is your best option. Send this fire truck, send these police cars, send this ambulance, this specific one, because of who's on it, what equipment they have, et cetera, et cetera. And that's bringing in, when Doug was talking about his data lake and, the right tool for the right job, that's where you really have to have that conversation, because without those kind of capabilities, it becomes extremely difficult to do that. And Doug, I don't know if you want to add anything to that, or Dallas, if you want to, tell me I didn't answer your question, but Doug, you got anything?
No, I think that answered it really well. And yeah, apologies, I kind of diverted from the original intent of that question, or comment really. But yeah, I mean, when you're talking about location data and getting immediate access, again, latency becomes that dominant metric again. And because of that, the right system to empower that, whether it be a NoSQL database, whether it be a purpose-built graph database, or a purpose-built like DAG style solution to get to the question, the answer you need, that's going to lower latency. All of those things that lower query time processing are going to lower latency, and that's where you can get more and more real time in terms of your decision making and the information that's coming back to you.
Excellent. Oh, looks like another message coming here. All right. Well, guys, I think we've gotten pretty close to the end here. Maybe I can throw one more question out here for you, and we'll just we'll see where we're at. Okay. How can cloud solutions / applications best be leveraged if you have limited connectivity? I don't know about the rest of y'all, but I live in Idaho, which is rurally near the middle of nowhere. And we have a real issue with connectivity. In fact, I remember several of my customers out here in the Idaho, Montana area that have one way in, one way out, right? So they have some real connectivity issues. How can they take this approach of cloud-based solutions and applications?
Yeah, I think that's an excellent point, and one that's really common here as a trend in public safety, because many of the public safety agencies are in rural locations, and so connectivity needs to be supported in those locations as well, and that's where we do see again a shift towards wireless connectivity. So LTE, 5G, satellite, all working and working pretty well as a primary means of connectivity, and again, I think that's a trend we'll continue to see moving forward, because laying fiber into some of those areas is very difficult, and over the air just makes more sense with the technology that's available. So I think we'll see continued investment in like satellite connectivity, in 5G connectivity, and also still in LTE, because the range of LTE works really well. So I think that's one thing. But the other thing that John and I are doing are working with application providers to be able to support better better application needs and a better experience on an application, even in periods of intermittent connectivity. So it's certainly possible to design an application where, let's say your connectivity is going to go in and out, frequently. That's okay. If you can do it in a way where, when you do get connectivity back, you get the right amount of information back, and you get it back in a sort of a non-overwhelming way to the end user, then you can still continue on and perform those operations. Now, obviously, the real-time nature will be, a victim sometimes of that intermittent connectivity, but it can still work, and you don't have to like constantly refresh your page or have a poor user experience because the application is expecting some constant high bandwidth, low latency connection. Some applications need that, and they're just going to have that because of the nature of the application, but not all applications do. And again, it's the way you design the application to, if you know that intermittent connectivity is coming, that's okay. You design for it and you handle it and still give the end user a solid experience.
Excellent answer. We run across that a lot in public safety, especially in the side of the communications network. I know that the idea of like wireless relays and so forth, and broadband connections, that's really a key for some of these folks that only have one way in, one way out with a cable. And sometimes it's only, it's very thin band. When I grew up in Alaska, we used to call it the information super garden hose. So, you could actually see when you try to pull in, imagery files, the bulge of information coming through the internet cable. So yeah, I appreciate what you guys are doing. It's excellent having you guys in here today, and thank you so much for participating. Thank you everybody for sitting in today. And if you do have any other questions or want to get back in touch with Doug or John, their contact information is there on the screen. Gravel will capture that, and we will save this recording for posterity. Doug, you did a great job.
Awesome. Thanks everybody for joining us. Appreciate it.
Thank you, everybody. Stay safe. Take care. Appreciate what
Thanks
you do.
so much. Bye-bye.